got some fresh images of 3I Atlas, the third ever interstellar object observed from Earth.
The James Webb Space Telescope turned its infrared vision toward interstellar object 3I Atlas and revealed something that immediately startled astronomers. The imaging campaign was meant to refine observations of its dusty tail, its compositional spectrum, and its unusual speed as it passed through the inner solar system. Instead, what was captured was a set of strange acceleration patterns, subtle shifts in motion that could not be explained by ordinary gravitational interactions alone. This moment instantly became a landmark in modern astronomy as the telescope's precision pulled into focus a behavior that had only been hinted at before in previous interstellar visitors. Webb's unparalleled sensitivity across infrared bands allowed researchers to isolate faint outgassing plumes and directional drifts that standard telescopes could not resolve, offering the most detailed look yet at a truly alien body moving through our neighborhood of space. Before we start, smash the like and subscribe buttons for more updates. The acceleration patterns spotted near 3I Atlas carried with them a profound mystery. Unlike comets born within our solar system, whose accelerations are often tied to sublimating ice and dust jets, this object displayed erratic thrust-like deviations in multiple directions. Webb's infrared detectors traced the thermal glow of gases being expelled, but the geometry of the emissions did not match the straightforward tails seen in most comets. Instead, there were asymmetries that suggested either a highly unusual structure or an internal process unfolding inside the nucleus. This was not a clean curve of acceleration caused by the sun's heat nudging material away. It was a jagged sequence of accelerations, pauses, and even reversals in trajectory strength. Such an irregular signature hinted at an object with properties completely different from any natural comet cataloged to date. Infrared imaging was the key to unlocking these details. Webb's ability to peer into the warm spectra of escaping molecules allowed astronomers to see carbon compounds, exotic ices, and even silicate grains glowing faintly against the black background of interstellar space. These emissions did not form a single tail but instead fanned out in strange arcs, each linked to small shifts in the object's velocity. Scientists could literally map the changes in speed and direction to the timing of particular outgassing events, creating a direct connection between chemistry and motion. What made it even stranger was the composition itself. Molecules not commonly found in comets within our system, suggesting that 3I Atlas was carrying the chemical fingerprint of a stellar nursery far different from the one that birthed the sun. As the telescope kept its gaze fixed, a pattern began to emerge. The object would release material in bursts, sometimes concentrated along one axis, then switch suddenly to another direction. Each burst aligned with spikes in acceleration that pulled the body ever so slightly off a gravitationally predicted path. Normally, comets slowly drift in response to solar heating, but here the changes were sharp and almost rhythmic. This rhythm is what first captured attention. It was as though the object pulsed with some hidden mechanism, expelling matter in intervals that created a dance of acceleration through interplanetary space. The predictability of the timing was as fascinating as the unpredictability of the directions. One implication of this discovery is that interstellar objects may carry within them internal structures capable of storing energy in unusual ways. Perhaps crystalline lattices trap volatiles until pressure builds to a threshold, releasing them explosively in localized jets. Alternatively, the object could contain cavernous voids that channel heat unevenly, causing vents to open and close like valves. Webb's infrared spectra provided hints of temperature gradients across the nucleus, which could support the idea of a fractured interior with heat moving in unpredictable ways. These findings suggest that interstellar comets may not simply be frozen rocks adrift between stars, but dynamic, evolving travelers whose journeys reshape them continuously. The acceleration anomalies carried another implication as well, the possibility of non-natural processes shaping the motion of the object. While most scientists lean heavily toward natural explanations, the regularity of the acceleration bursts inevitably stirred curiosity. Webb's data showed that some accelerations occurred without a corresponding infrared signature of gas release, which raised the question of whether certain shifts were due to forces beyond sublimation alone. This line of inquiry remained cautious, but it underscored how Webb's sensitivity forces astronomy to confront anomalies rather than dismiss them. If natural processes were at work, they had to be processes not yet fully understood. From a broader perspective, Webb's imaging transformed 3I Atlas into more than just a visitor. It became a probe of galactic diversity. Each interstellar object carries the chemical and physical legacy of its birthplace. And in this case, the infrared glow revealed a recipe of compounds pointing to a system enriched with carbonaceous material. The accelerations then added another layer of story. The structure of the body was not monolithic but fractured, layered, and responsive in ways alien to us. When scientists speak of cosmic archaeology, they mean exactly this, using fragments of other star systems as relics to reconstruct how planets and comets form elsewhere in the galaxy. The strange accelerations became clues not only to the mechanics of this object, but also to the history of its origins. The precision of Webb also allowed astronomers to trace the object's trajectory with unprecedented accuracy. By correlating infrared emission patterns with deviations in orbit, they could model how much mass was lost in each outburst and how that loss translated into acceleration. These calculations revealed that 3I Atlas shed material in short, powerful spurts rather than a steady flow. Such behavior means that the body might survive longer in interstellar travel than if it bled material constantly, preserving volatile compounds for billions of years until reaching another star's domain. The survival of such compounds is critical, as it offers a potential mechanism for distributing prebiotic chemistry across the galaxy. The implications ripple outward into the question of panspermia. If objects like 3I Atlas are common, carrying exotic organics and releasing them in bursts, then they may act as couriers of chemical building blocks between stellar systems. Webb's infrared detection of organics tied to acceleration patterns shows how these molecules can be shielded for long journeys and then liberated suddenly when heated near a star. Each burst of acceleration becomes not just a quirk of physics, but a delivery event, scattering complex molecules into new environments. The possibility that interstellar comets contribute to seeding planetary systems with chemistry necessary for life is strengthened by observations such as these. There is also the matter of how such findings refine our models of celestial mechanics. Traditional orbital models assume smooth, predictable forces, but Webb's revelations show that real interstellar objects can behave like chaotic thrusters, nudged this way and that by internal processes. This has consequences for predicting future paths and for planning potential missions to intercept similar objects. If an interstellar comet can accelerate unpredictably, spacecraft trajectories must be designed with greater flexibility. Webb's data will serve as a guide for mission planners, teaching them how to anticipate sudden deviations and still carry out rendezvous or flybys successfully. The community of astronomers also recognized that this event highlighted the value of infrared observations over visible light studies alone. Previous interstellar visitors like Oumuamua sparked debate because telescopes could not capture the faint signatures of outgassing, leaving unexplained accelerations in a fog of speculation. Webb, with its infrared instruments, cut through that fog and provided direct evidence of thermal emissions tied to motion. The result is a new standard for studying such visitors. Without infrared data, the story is incomplete. This lesson will shape the strategies for observing future interstellar bodies that pass through our system. In a sense, 3I Atlas became a laboratory for testing how alien ice behaves under sunlight. The accelerations acted like markers of chemical transitions, each burst representing a threshold crossed inside the nucleus. Webb's imaging traced these thresholds across time, creating a timeline of thermal evolution. This timeline helps astronomers model not just this object, but any body exposed to stellar radiation after eons in the cold. The interplay of heat, chemistry, and motion becomes clearer when seen through the lens of an object with no evolutionary tie to our solar system. The sheer strangeness of the acceleration patterns also inspired a reconsideration of how interstellar objects form in the first place. If the interior of 3I Atlas is so fractured and volatile rich that it behaves in this jagged way, then perhaps the processes in its home system favored rapid formation, quick trapping of gases, and violent ejection into space. This points toward turbulent protoplanetary disks as nurseries for such bodies, environments where collisions and rapid cooling could lock away materials that later erupt in chaotic fashion. Webb's data, then, is not just about one object's present, but about the ancient storms of creation that forged it. Webb's contribution to this discovery also underscores the telescope's broader role in astronomy. Its infrared imaging was designed to look back to the first galaxies, but here it applied the same sensitivity to something passing right next door. This dual role, probing the distant universe while scrutinizing local anomalies, illustrates the versatility of the instrument. The strange accelerations of 3I Atlas remind us that frontiers of knowledge lie both billions of light years away and within the transient paths of objects crossing our own skies. The findings also had implications for planetary defense and our awareness of celestial dynamics. Although 3I Atlas itself posed no threat, understanding the mechanics of unpredictable acceleration is vital. If a body were ever on a potential collision course, unexpected deviations could alter predictions in dangerous ways. Webb's data highlights the importance of monitoring not just orbits but also the subtle physical processes that shape them. Being able to model outgassing-induced acceleration could become a tool for assessing risks in the future. There is a philosophical resonance to the event as well. To watch an object born around another star behave in ways we do not fully understand forces us to acknowledge the vast diversity of nature. Our solar system is only one template, and visitors like 3I Atlas show us that other templates exist, carrying rules and patterns alien to us. Webb's infrared revelations are not merely scientific results, they are reminders of humility, of the need to expand our imagination to encompass phenomena we cannot yet categorize neatly. What is perhaps most captivating is the sense of motion Webb conveyed. In the infrared glow, 3I Atlas did not appear as a static point, but as a restless traveler shedding material, twitching in its path and marking its journey with acceleration bursts like heartbeat pulses across space. This dynamic picture transforms interstellar objects from curiosities into characters, with behaviors, quirks, and mysteries of their own. The telescope gave the world not just data, but a narrative of movement, a chronicle of a stranger passing through. As the imaging campaign concluded, the data left astronomers with a wealth of modeling opportunities. Each acceleration point became a puzzle piece to be fitted into simulations of cometary dynamics, chemical evolution, and interstellar transport. The details are still being parsed, but one thing is clear. The strange accelerations spotted near 3Y Atlas have expanded the scope of what interstellar astronomy can uncover. They push the boundaries of our models, challenge our expectations, and remind us that the cosmos always has surprises waiting when we dare to look closely enough with the right tools. The Webb telescope's infrared campaign on 3I Atlas not only reshaped scientific expectations, but also opened up new dimensions for interpreting what it means to encounter matter forged in a different corner of the galaxy. Each photon captured by the telescope told a story that was simultaneously chemical, mechanical, and cosmic. To move beyond the immediate strangeness of the acceleration patterns, one must explore the cascade of consequences for astronomy, planetary science, and even cosmology itself. The observations form a lens through which the very processes of interstellar transport, star system dynamics, and matter evolution can be reconsidered with new urgency. At the heart of the analysis lies the interplay between thermal physics and structural geology. Webb's ability to detect subtle emissions at multiple infrared wavelengths made it possible to reconstruct a map of surface temperatures across the body. Those temperature gradients hinted at an uneven crust, fractured and porous in ways that encouraged venting in sudden spurts. But beneath this geological model is a deeper implication, that interstellar comets may record the violent history of their parent systems, storing within their fractured interiors the echoes of collisions, rapid cooling, and chaotic migrations that characterize their birth. If one object passing through our solar system shows such complexity, then the galaxy may be filled with countless others shaped by unique stellar histories, each carrying its own suite of volatile chemistry. The acceleration signatures also reframe our approach to dynamical models of small bodies. Traditional celestial mechanics relies on gravity as the dominant force, with secondary corrections for radiation pressure or predictable outgassing. What 3I Atlas revealed, however, is that acceleration can be jagged and discontinuous, with pulses that resemble engineered propulsion more than natural drift. This forces theorists to rethink how to model the trajectories of interstellar bodies. Predictions must now incorporate stochastic processes, irregular venting cycles, and the possibility of unseen internal reservoirs. These refinements are not academic alone. They will directly affect how we plan interception missions for future objects, ensuring that spacecraft can adapt to sudden deviations rather than miss their targets due to oversimplified assumptions. Another significant dimension of the discovery lies in comparative analysis with earlier interstellar visitors. The first, Oumuamua, sparked fierce debate precisely because its acceleration could not be linked to visible outgassing. Some argued for unusual hydrogen sublimation, others for radiation pressure acting on a thin sheet-like body. With 3I Atlas, Webb's infrared vision conclusively tied accelerations to detectable emissions, but the irregular patterns added layers of complication. Now, researchers have two distinct data points: one object with unexplained smooth acceleration and another with chaotic bursts of acceleration. The implication is that interstellar objects are not a monolithic class but a diverse population, each with its own structural quirks. This diversity is vital. It means the Milky Way likely hosts a zoo of such wanderers, each one a messenger of alien geologies. From a chemical standpoint, Webb's detection of exotic organics places 3Y Atlas in a category distinct from typical solar system comets. Compounds with unusual bonding states glowed in the mid-infrared spectrum, suggesting a synthesis environment under different radiation conditions. This points toward a stellar nursery, with more carbon-rich dust, perhaps orbiting a younger, more massive star where chemical reactions proceeded differently than in our own protoplanetary disk. Such chemical signatures are more than curiosities. They are blueprints of galactic chemistry. By studying the irregular accelerations in parallel with these organics, scientists realized that the bursts of material being expelled were also bursts of information, releasing the story of another system's formation directly into our detectors. The physical irregularities of 3I Atlas also raised questions about the survivability of such objects across vast cosmic distances. An object fractured and volatile rich might be expected to disintegrate during interstellar transit, yet here it was, intact enough to surprise us. This paradox suggests that conditions in interstellar space, far from stellar radiation, act as a preservation chamber. The object could drift for millions of years with its fragile structure stabilized by cold and vacuum, only to awaken violently when encountering the warmth of a new star. Webb's images of sudden accelerations reflect this awakening, a kind of interstellar hibernation broken by a solar alarm clock. Such survivability makes it more plausible that volatile, rich bodies could transport chemistry between systems without losing their essential makeup along the way. In this way, 3I Atlas becomes a test case for galactic panspermia scenarios. If volatile-laden comets can survive intact and then distribute organics in bursts, the mechanisms for spreading prebiotic ingredients across light years become tangible. Every acceleration burst captured by Webb is not just an alteration in orbit, it is a dispersal event, a scattering of alien chemistry into a planetary system that may host habitable environments. The telescope thus captured not only the mechanics of motion, but also the mechanics of delivery, where cosmic couriers distribute their packages unpredictably, yet effectively, wherever their travels take them. There is also the methodological breakthrough that Webb's observations represent. Infrared imaging was not simply a matter of detecting heat. It was about connecting emission spectra directly to dynamical consequences. For the first time, scientists could pair the spectral fingerprint of escaping gases with measurable changes in trajectory. This union of spectroscopy and astrodynamics marked a leap forward in methodology. It meant that acceleration was no longer a mysterious external measurement, but an internal property of the object itself, directly tied to its chemical and structural nature. Future studies will undoubtedly use this approach as a template, applying the same dual analysis to every interstellar object discovered. On the theoretical frontier, the irregular acceleration patterns feed into debates about the limits of natural explanation. While most researchers emphasize exotic natural processes, a small but persistent subset considers whether any observed behavior could resemble controlled propulsion. Webb's data did not provide definitive evidence for such an interpretation, yet the rhythmic bursts of acceleration inevitably stirred speculation. Whether or not one entertains the possibility, the fact that a natural object can mimic the appearance of engineered motion forces astronomy to refine its criteria for distinguishing the two. In other words, 3I Atlas provided an invaluable calibration point for the search for techno-signatures, reminding us that nature often performs tricks that look artificial unless studied with sufficient depth. The presence of acceleration without corresponding emission signatures in certain moments deepens the enigma. If Webb could not detect outgassing during specific shifts, alternative mechanisms must be considered. One possibility is dust grains or non-volatile fragments being ejected without thermal emission, exerting subtle but real thrust. Another is that internal stresses caused sudden structural collapses that altered mass distribution, changing rotation and inducing apparent accelerations. Each possibility expands the field of cometary physics, inviting models that are more nuanced than the outgassing explanations long relied upon. Webb's observations thus serve as a crucible where traditional cometary science is tested against unprecedented anomalies. The broader implications extend to the population statistics of interstellar objects. If 3I Atlas is representative of a subset characterized by erratic accelerations, then surveys must account for this when estimating frequencies and detection rates. Accelerating bodies may appear dimmer or brighter depending on venting orientation, making them harder to catalog consistently. Webb's revelations suggest that surveys with only optical data may underestimate the diversity of interstellar objects, as their unusual dynamics cause observational biases. This compels astronomers to design future surveys with infrared capacity, ensuring that we do not miss whole classes of visitors whose behavior departs from the norm. One of the most exciting scientific consequences of this discovery is the way it enriches planetary formation theory. The fractured structure implied by the acceleration suggests rapid accretion processes in a chaotic disk, with collisions embedding volatile reservoirs unevenly. Such conditions might differ dramatically from the relatively stable growth of bodies in our solar system. If interstellar objects are indeed messengers from more violent nurseries, then planetary system diversity across the galaxy may be far greater than anticipated. This has implications for everything from planet sizes to atmospheric compositions, as the raw building blocks vary according to the chemistry and dynamics of their birth environments. Webb's contribution also highlights the role of timing in scientific breakthroughs. The telescope was operating at peak performance, able to lock onto a faint moving target, track it across the sky, and collect long-exposure infrared data. Without that capability, the accelerations might have gone unnoticed, written off as measurement error. Instead, the telescope's design allowed humanity to see what had been invisible for decades of comet studies: the heartbeat-like pulses of an interstellar traveler responding to solar heat. This underscores a truth about astronomy: that technology defines discovery. The universe has always been strange. Only now do we have the instruments sensitive enough to recognize that strangeness directly. The discovery also adds urgency to the search for more interstellar bodies. If two such visitors in a short span have yielded such mysteries, then the cosmos may be brimming with them. Webb's success will likely drive investments in wide-field infrared observatories optimized to detect faint, fast-moving points of light that betray alien origins. Once detected, Webb and other space telescopes can zoom in, applying the template refined with 3I Atlas. Each new visitor becomes a data point in a growing statistical tapestry, revealing the hidden diversity of extrasolar systems. There is a cultural and existential dimension as well. Watching a fragment from another star system behave so differently from anything native to ours stirs a sense of connectedness across the galaxy. These are not just rocks. They are ambassadors of distant suns, carrying in their irregular movements the rhythms of alien creation. Webb gave us a glimpse of that rhythm, a pattern of accelerations that spoke of conditions foreign yet intimately tied to our shared galactic environment. The implications go beyond science, reminding us that the cosmos is not homogeneous but alive with variety, surprise, and motion. As researchers continue to model the data, one key realization is that the strange accelerations may hold the key to reconstructing the interior architecture of 3I Atlas. Each burst acts like a probe, revealing which cavities vent, which surfaces fracture, and how internal heat is distributed. By analyzing these bursts, astronomers can reverse engineer a three-dimensional picture of the interior, a feat never before achieved with an interstellar body. This transforms erratic accelerations from curiosities into diagnostic tools, turning chaos into information. The telescope's ability to track these bursts provides the blueprint for a new subfield of interstellar tomography. The long-term implications stretch into cosmochemistry. If interstellar comets are carrying volatile-rich payloads and releasing them in bursts, then the galactic medium itself is enriched not just gradually, but episodically. Each pass through a star system becomes a seeding event, injecting complex molecules into regions where planetary disks may form later. The accelerations observed by Webb are not just mechanics, they are part of the galactic circulation of matter, the great cycle by which star systems exchange ingredients. This turns every interstellar object into a participant in galactic ecology, shaping the chemical landscape in which new stars and planets arise. There is also an evolutionary lesson. If comets like 3I Atlas fracture and vent in chaotic ways, they may represent a later stage in the life cycle of interstellar debris. Younger bodies may travel intact with smooth surfaces and predictable sublimation. Over time, collisions, radiation, and internal stresses fracture them, leading to the erratic accelerations Webb observed. If this hypothesis holds, then the diversity of interstellar accelerations reflects an age sequence, a way to measure the maturity of an interstellar traveler. Webb's data could thus provide the first clock for dating such bodies, an astronomical chronometer based on motion. In terms of human exploration, the discovery sharpens our imagination for what missions to interstellar objects might encounter. A spacecraft approaching 3Y Atlas would not meet a stable, slowly venting comet but a dynamic body, shifting unpredictably, venting in bursts, and altering its spin. Such conditions pose engineering challenges but also opportunities. Instruments on board could measure bursts directly, sampling freshly exposed material from deep within. The Webb telescope has thus set the stage for designing missions that do more than fly by. They could ride the pulses of an alien traveler, probing its secrets in real time. The story of 3I Atlas under Webb's gaze is therefore not just about one object, but about the expansion of a field. Interstellar astronomy, once a hypothetical discipline, has become real, anchored in data of unprecedented detail. The strange accelerations are not outliers but harbingers, signs that the galaxy's travelers carry within them complexities we are only beginning to understand. The telescope's revelations mark the dawn of a new era, one where each visitor is a window into the diversity of worlds beyond our own. The Webb telescope's encounter with 3I Atlas left astronomers with a puzzle that extended far beyond cometary science. What began as a close examination of acceleration anomalies grew into a multidisciplinary conversation that stretched across astrophysics, planetary geology, chemistry, and even fluid dynamics. Each new dataset pressed scientists to expand their frameworks, because nothing about this object behaved in ways entirely familiar. In many respects, 3I Atlas became a mirror reflecting the limits of our models, revealing gaps in understanding that had gone unnoticed until this extraordinary object arrived. One of the most striking features was the relationship between light scattering and motion. As Webb tracked thermal radiation, it also captured how dust grains disperse through space in unusual geometries. Normally, a comet's dust tail streams predictably along vectors shaped by sunlight pressure and the solar wind. Yet, around 3I Atlas, the dust formed patchy clouds and cross-currents, patterns that resembled turbulent flows rather than smooth streams. These irregular dust morphologies were synchronous with sudden accelerations of the body, suggesting that the mechanics of dust release and the dynamics of the nucleus were tightly intertwined. This made clear that interstellar objects could not be fully understood without integrating both microscopic particle behavior and macroscopic motion into a single model. A second layer of intrigue emerged from the rotational dynamics. Webb's infrared data, when combined with ground-based measurements of reflected light, showed that 3Y Atlas rotated in a highly chaotic manner. Instead of spinning steadily along a principal axis, it tumbled unpredictably, as though torque from asymmetric jets was constantly nudging it off balance. Each irregular acceleration fed back into its spin, producing a self-reinforcing cycle of instability. This dynamic highlighted an underexplored area of celestial mechanics, the coupling of outgassing events to rotational states. By tracing this coupling, scientists gained insight into how small bodies can evolve rotationally over long timescales, potentially fracturing themselves or reshaping entirely. Such rotational chaos also raises the possibility that interstellar comets contribute fragments to the galaxy more frequently than anticipated. A body that tumbles and fractures under its own venting may release splinters, which then drift separately as smaller travelers. These fragments could account for populations of faint, undetected interstellar debris moving through space. Webb's ability to see the signs of structural stress makes it possible to connect visible acceleration anomalies with broader questions about how the galaxy seeds itself with cometary shards. On the chemical side, Webb's mid-infrared instruments revealed peculiarities that resist simple classification. Absorption lines in the spectra suggested compounds that do not match common solar system ices. Some appeared to be nitrogen-rich organics with complex backbones, while others pointed to silicates with unusual lattice defects. These materials not only explained part of the erratic venting, but also suggested a protoplanetary disk environment rich in energetic radiation. If 3I Atlas condensed in a system bathed in ultraviolet or X-ray emissions from a young star, then its chemistry would differ radically from comets formed in quieter nurseries. Such findings give astronomers their first direct evidence of interstellar chemical diversity, with implications for the types of atmospheres exoplanets in those systems might eventually host. If you liked this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on strange acceleration patterns near 3I Atlas? We want to hear from you. Thank you for watching and see you next time.